Today, I'm at the University of Warwick to take a look at nuclear magnetic resonance spectroscopy. You may recognise this as an NMR spectrum. I also hope you remember that the different patterns of signals and their positions along this chemical shift scale tell us something about the chemical environment of the nuclei being examined. In this case, it's a proton NMR spectrum. This is one NMR laboratory in the Department of Chemistry, and I'm here to show you a typical NMR instrument and some of its capabilities. I also hope to indicate just how powerful and sophisticated the NMR method has become. We'll concentrate on proton NMR spectra, as you learned quite a lot about carbon-13 NMR spectra in your second level course. Let's start with a schematic of the instrument itself. If we wish to excite nuclei from a low energy spin state to a higher one, first we must place our sample containing those nuclei into an environment where the nuclear spin states have different energies. That means in a strong magnetic field. In real life, the superconducting magnet is in here. It's cooled with liquid helium to near absolute zero and carries a large current isolated from the outside world. Now, we must provide energy to stimulate transitions between the lower energy state and the higher one. The appropriate energy falls in the radio frequency range. In this instrument, we apply a short, powerful pulse that encompasses all the frequencies of interest, and this pulse, lasting just a few microseconds, is applied at right angles to the magnetic field, exciting all nuclei simultaneously. The net magnetization of the sample, aligned with the field before the pulse was applied, is tipped through an angle, often 90 degrees. The coil then monitors the oscillating magnetism as it relaxes back to its pre-pulse equilibrium value. This takes a few seconds. The signal obtained is called an FID, free induction decay, which consists of exponentially decaying sine waves, with frequencies corresponding to the resonance frequency of each nucleus excited. If all nuclei are equivalent, as in this case, for cyclohexane, the FID is a simple sine wave decaying to zero. Using a routine known as Fourier transformation, the computer converts this intensity versus time plot to the standard spectrum format of intensity versus the single cyclohexane frequency. More usually, compounds have spectra with closely spaced lines. Then, the sine waves from all relaxing nuclei are superimposed, giving a complex FID showing a distinctive pattern. Such a pattern is similar to an interferogram in FTIR, but all we have to appreciate is that, as in IR, Fourier transformation can produce from it a spectrum in standard format. In another parallel with FTIR, all protons in FT-NMR are observed at the same time, so acquiring a spectrum is fast. However, NMR is inherently insensitive, so we tend to subject each sample to a number of pulses, each followed by a few seconds of data acquisition. The computer then adds together successive FIDs to build up a strong signal before carrying out the Fourier transformation. Let's take a closer look at sample preparation. Mostly, compounds are examined in solution, often with deuterated chloroform, CdCl3, or D2O as solvent. My colleague, Dr. Oliver Howarth of the NMR Centre at Warwick University, is making up an appropriate solution. It contains milligram or microgram amounts of sample, depending on the nuclei being examined and the instrument used. It's placed in a long, narrow tube fitted with a spinner. Once placed carefully into the instrument, the solution is exactly in the middle of the magnetic field, and jets of air directed against the spinner rotate the tube. This effectively increases the uniformity of the magnetic field because the spinning action ensures that molecules experience an average field. This is the FID for sucrose. And here is the corresponding conventional proton NMR spectrum. The area under each of these signals is proportional to the number of protons causing each resonance signal. The computer can give us this invaluable information by integration, which appears as digital printout or as a step trace on the spectrum. For example, this singlet has an integration that's twice that of this doublet of doublets. There are twice as many protons causing this signal as cause this one. In fact, this corresponds to a CH2 unit and this to a single CH proton. Incidentally, this large off-scale signal is due to water, strictly HDO, formed mainly by the exchange of sucrose hydroxylic protons with the D2O solvent. This exchange process also explains why we don't see protons of the individual hydroxyl groups of sucrose in the spectrum. The NMR spectrum of sucrose would not appear like this when recorded on any NMR instrument. This sequence shows NMR spectra of the same sugar recorded with different types of instrument. Can you see what's happening? As the magnetic field strength decreases, and hence the applied frequency decreases, the patterns are becoming less discrete. In this spectrum, the patterns are complex and distorted. It's called a second-order spectrum. This happens when the spin-spin coupling constant between groups of neighboring nuclei has a similar value to the difference in their chemical shifts. A first-order spectrum of discrete, familiar patterns occurs when the coupling constant is much smaller than the chemical shift difference. So why is this affected by the field strength? Well, coupling constants don't vary with field strength, but chemical shifts in Hertz increase with increasing field strength. So as we use higher field magnets, we are more likely to obtain simple first-order spectra because patterns due to different groups of nuclei move further apart in frequency, but their coupling constants remain the same. From a complex second-order 60 MHz spectrum, we've moved to a much simpler 400 MHz spectrum that's nearly first order. Without worrying about precise interpretations, you'll be able to recognize familiar and interpretable patterns like a singlet, a doublet, and a doublet of doublets, for example. Simplification of spectra is one good reason for preferring high-field NMR instruments. Another reason concerns sensitivity. The nuclear spin states separate further in energy as the applied field increases, with the result that larger numbers of nuclei reside in the lower energy state. The greater the population of nuclei that can absorb the RF radiation and then subsequently relax, the stronger the FID signal. In other words, the higher field instruments are more sensitive, allowing smaller amounts of material to be handled. This is important, particularly when working with low abundance isotopes like carbon-13. Let's illustrate another use for NMR spectroscopy. Imagine that you've synthesized a chiral compound of which only one enantiomer is of use to you, say this compound. The NMR spectra of these and all pairs of enantiomers are identical, and hence can't be used to find out the relative amounts of the two enantiomers. But if we add one enantiomeric form of a chiral reagent known to shift NMR signals, a so-called shift reagent, it complexes with the sample molecules, forming two diastereomeric complexes. Being diastereomers, these have different physical properties, unlike the original enantiomers, and hence different NMR spectra. This partial spectrum shows the methyl group singlet split into two in the presence of the chiral shift reagent. The integral tells us that each enantiomer has equal intensity. That is, this sample is a 50-50 racemic mixture of the two enantiomers. A different sample of the same organoiron compound shows one enantiomer in excess over the other. In fact, the integral tells us that in this case, the ratio of enantiomers is 75 to 25. This sophisticated analysis was made possible by the chemistry of shift reagents. But NMR spectroscopy can also gain great sophistication through application of instrumental tricks. In a short video sequence, we can't do full justice to the power and range of NMR methods, but I want to give you an indication of the more exotic experiments and an inkling of their value. Don't worry about details, just appreciate the power. Here, in the 400 MHz spectrum of sucrose, it's not obvious which set of nuclei is coupled to which other nuclei, but we can find out by single frequency spin decoupling. Let's find out if there are any signals spin coupled with this doublet on the left-hand side. If we irradiate the sample with an RF field at the frequency of the doublet's chemical shift, the protons causing the doublet resonate between their two states so rapidly that any protons that are coupled can no longer distinguish their neighbours' separate energy states. The signal due to the irradiated protons almost disappears, and signals due to previously coupled protons collapse to a simpler form as they can no longer couple with their neighbour. For example, this doublet of doublets collapses to a doublet, allowing us to interpret the spectrum more easily and telling us unambiguously that these two signals are coupled together. There's another way of deciding which NMR resonances are coupled together, and it's particularly valuable when solving very complex structures. We don't subject our sample to one pulse per FID, rather we use a sequence of pulses before acquiring an FID. In generating pulse sequences, we could vary the number of pulses, the power of each pulse, and its type, for example, frequency and amplitude, and we could vary the time interval between pulses. In this particular pulse sequence, protons that are coupled are readily determined via a contour plot. There are two identical chemical shift axes, and signal intensities are shown as contour lines. Here, the conventional spectrum of sucrose is represented as a contour plot on the diagonal line. To help you see this more clearly, we've also reproduced it in the familiar form here at the side of the plot. Now, which of these resonances are coupled to which? Note that there are signals off this diagonal that are symmetrically disposed about it. If two of these form the corners of a square when taken with two signals on the diagonal, then those two signals must be coupled. Look again at this left-hand doublet. It's coupled to the doublet of doublets here because there's a squared pattern based on them. On the other hand, this resonance is not coupled to any of the others because it doesn't form a squared pattern with any of them. Of course, this is the HDO signal, so it makes sense that it can't be coupled to any sucrose signal. Close examination of this plot would tell us all the coupling relationships in the whole spectrum. When spectra are complex, this information is invaluable for spectral interpretation. There's another program of pulses that can determine the spatial proximity of nuclei, whether or not they're coupled. Such methods are now routinely accessible and make NMR spectroscopy a tool of considerable power and flexibility. In a short video sequence, we haven't been able to cover all the capabilities of NMR spectroscopy. For example, protons and carbon-13 nuclei aren't the only ones that can be observed. At Walton Hall, we also use boron and silicon NMR in some of our research. Here at Warwick, oxygen, vanadium and molybdenum are often examined with this instrument. Just like mass spectrometry, the NMR technique is still expanding and growing in power as a method for elucidating structures.